గోలైలోకి వెళ్తేనే అది ఇప్పుడు ఎండ్ స్ట్రీమ్ ఎడిట్ స్ట్రీమ్ అది వస్తుంది. మళ్ళీ అది క్లిక్ చేస్తే క్లోజ్ చేయాలి. ఇప్పుడు ఎండ్ స్ట్రీమ్ కొట్టాలా? ఒక్క నిమిషం ఒక్కసారి ఎన్ని డిస్క్లోకి రా. నువ్వు ఫస్ట్ కొట్టావు నువ్వు. సార్ మీరు స్టార్ట్ చేయండి సార్. స్టార్ట్ చేయండి సార్. మీరు
ఎట్లా స్టార్ట్ చేయాలి?
6:53 అవుతుంది సార్. 7 అంటారు.
మీరు కెమెరా ఆడు ఉండాలిగా
సార్.
అక్కడ ఉండి
అది రెడీ ఉంది సార్. అంతా ఓకే.
స్టార్ట్ చేస్తే అయిపోతుందా?
స్టార్ట్ చేయడమే సార్.
నిజమా?
అవును సార్. పెట్టినా వస్తుందా?
మీరు ఒకసారి చెక్ చేయాలి. వాయిస్ వస్తుందా? Okay. Good evening, students. In this session, let us see what are the important topics in analog circuits and the leftover PYQs. Last session we have seen some PYQs. So we will continue from there, okay? So what are the models to memorize? Now students keep asking, right, sir, should I prepare short notes for this subject? What should I remember before I go to the exam, right? There is no need for you to remember anything in this subject except these models, right? So these models are very handy. Now, as I told you in my last video also, here we are interested only in the terminal behavior of the device. We are not interested in the function of the device, because analog starts from the characteristics. So from the characteristics, I have a list here, and this list gives you the equivalent models of those devices or equivalent circuit. So whenever you find that device in the gate problem, you replace by this equivalent, apply some Kirchhoff's law, and then you will get the answer, right? So any problem, any gate problem, just this they are hardly 2 pages. So any gate problem can be solved from this 2 pages. So this is the summary, the whole summary of analog circuits, right? So let's see. If given a problem, you will find a resistor R, right? A resistor of R ohms. Then the value is not going to change whether there is a DC analysis or signal analysis. The reason is resistor will obey an equation y equal to mx, right? So y equal to mx or v equal to Ri. So what is R? R is V by I, and R is same as dV by di. R is V by I and R is same as dV by di. So resistor is not going to change its phase whether it is DC analysis or AC analysis. So resistor is the only component, probably is the same for DC and AC. Now if you find capacitors and inductors and say you want to solve filter problems, right? So there's an op-amp given and some resistors, capacitors and inductors. And how do you solve filter problems is by these simple switches. Whenever you find a capacitor for DC analysis or for low frequency analysis, you replace capacitor by open circuit. And for AC analysis, you can replace it by short, right? Somewhere in the high frequency or the mid frequency, you can replace capacitor by short. So the simple idea can allow you to score marks, right? Now inductor will give you a totally complementary picture as compared with capacitor. So inductors are replaced by short, capacitor by open, and the simple idea, you can solve filter problems in gate, right? Then when it comes to diode, what do? If the diode is ideal, you can replace by short, or if the examiner says 0.7, V gamma 0.7, then you can replace the diode with 0.7. So with this simple idea of replacing with 0.7, you can solve so many circuits, like say rectifier. You can solve peak detectors, clippers, clampers, voltage multipliers, and so on. So anything that is associated with diode, just replace the diode with 0.7, take some current. If the current flowing through the diode is positive, then the diode is definitely on, right? So it's a simple logic. When current flows in a device, naturally we say the device is on, right? So it's common sense. So you replace a diode by 0.7, take a current, and the current should always point from anode to cathode. And if the current flowing through the diode is positive, then the diode is on. So with this simple idea, you can do rectifiers and peak detectors, clippers, clampers, and so on. But if you apply a small signal to a diode, then the diode equivalent, this is the static equivalent of the diode, right? The dynamic equivalent of the diode is replaced by a simple resistor, RD, whose value is eta Vt by capital ID, and Vt is given by examiner. Eta is not given by examiner, you can always take it as 1, right? And what is ID? ID is the diode current, right? So the AC analysis is totally decided by DC. So whenever you want to do AC analysis, the discipline is first conduct DC and then go for AC. So that's the discipline you have to follow for a diode or a BJT or a MOSFET. Even if you're asked to find AC, you have to conduct DC first, right? And then what about BJT? Now BJT is a two-terminal device. BJT is a three-terminal device, so which means there is a two-port here, input port and output port. So at least two elements are needed. So here at the input you have a diode here. So there is 0.7 volts here, right? So 0.7 between base and emitter. At the collector, your IC is beta IB or alpha IE, right? Where alpha is beta by beta plus 1, right? So whenever you find a BJT, you can replace and put this model, or directly keep the BJT just like that and take 0.7 and solve. So with this simple idea, you can do all DC problems of BJT. You can solve all the biasing circuits of BJT, and you can also solve current mirrors on BJT. So all that you have to do is just take 0.7 and solve. That's it, right? So this is BJT in at DC. Now, what is the diode equivalent for AC? The diode equivalent for AC is a resistor. So if you replace between base and emitter a resistor R pi here, then you are doing AC analysis. And what is R pi? You know beta by GM, and GM is IC by VT. And then there is a dependent source, GMVB. And if you want to include early effect also, then you have this R0, which is early voltage by ICDC, right? So this is BJT for what analysis? AC analysis. Now suppose if you find this little cumbersome, then you can do one thing. You can replace a transistor, you can remove a transistor and put a resistor. That is also, because this is something you are taught even in networks class, because if you have dependent sources and you want to find Thevenin equivalent of a dependent source, then what is the Thevenin equivalent of the dependent source is a resistor. There is no V Thevenin, you have only R Thevenin, right? So even a BJT, you can just replace it with a resistor, and that is much easier if you don't want to do by this model and apply Kirchhoff's laws. And mostly in gate problems, this R0 is infinite. This R0 is infinite, so it is easy also if you want to solve it. But otherwise, you just remove the transistor and replace it by a resistor. Now I'll tell you how to replace by a resistor. Take a fresh page here. Now if you want to replace a transistor by a resistor, then we know that at the base terminal there is R pi, at the emitter there is R pi by 1 plus beta. And why did I divide by 1 plus beta? Because Ohm's law says that resistance is voltage by current. So what is Ohm's law? Resistance is voltage by current. So if the current is small, then the resistance will be large. If the current increases by 1 plus beta times, then the resistance will decrease by 1 plus beta times. So current and resistance are inversely proportional for a certain test voltage that you are connecting. So more current, less resistance. Less current, more resistance. So here emitter current is large, so resistance is small. At collector, if there is no early effect, it's infinite or R0. Right? So for a MOSFET, if you want, there is no R pi, so there is infinite here, R0 or infinite, and here this is actually alpha by GM. So alpha you can take it as 1 for MOSFET, because MOSFET has a single current. So now if you ask me what good this simple logic is going to do. Now if you know the simple logic, the effort in the exam will be less, right? So you'll be using less effort. For example, if you have 3 resistors like this, 5K, 10K, 10K. Now the effort that you put to solve this simple circuit will be the same effort if you have a BJT here also, right? So what is the input resistance here? How do we solve this? Now we know these two are in parallel, right? So if you cut here and inject a current, the current is going to divide, so they are in parallel. So 10K parallel 10K is going to be how much? 5K. And this combination is in series, so 5K plus 5K is going to be 10K, right? Now this is quite a simple problem, but these type of problems will give you marks in GATE exam, but the only difference is there will be a transistor here. Now, if at all you are asked to find the input resistance, so what do? We cut here and we make it parallel. So similarly, if I want to cut him here, they say that the resistance seen at base is R pi, right? So you have 5K, 10K, and the resistance from base to ground is R pi. So now, these type of problems are given for 2 marks, right? So you can simply say that it's 10K parallel with R pi in combination with 5. So it is 5 plus 10K parallel with R pi. Now what if I change the transistor circuit, instead of base terminal, I connect it at emitter. You're asked to find input resistance. Now even sometimes such problems are even given for 15 marks also, 10 marks, 15 marks in ESE also. But intuitively you can solve this. So you can, all that you have to do is just cut him here, and the resistance seen at emitter is alpha by GM. So the input resistance here is going to be 5K, 10K, and here emitter to ground there is alpha by GM, and then you can solve it. It's not a. So if you want, you can replace this by small signal model, but that takes time, 1-2 pages you have to do. But otherwise, you can start replacing transistors by resistors with a simple logic called Ohm's Law. So Ohm's Law says that if you apply a voltage and take current, V by I is going to be the resistor. So the only difference is BJT has 3 terminals, so you can have 3 resistors, right? So that is the most fascinating thing about BJT. You have kilo ohms at base, you have ohms at emitter, you have mega ohms here. So that's the reason you can create infinite combinations, and you can have a number of topologies. So the base will be connected to emitter, emitter can be connected to collector, collector to base, so you can play, right? So multiple transistor problems also you can solve, because all that you have to do is just replace the transistor with a resistor and do it. And the same thing, collector, it is R0. So if you have a problem like this, where there is a collector terminal, then 5K, 10K, and if you cut him here, there's going to be R0. So R0 parallel with 10K plus 5K. So you can, so with this as a simple idea, you can do multiple transistor problems as well. That's okay. Now imagine, I'll give you some insight. Now if you're not happy with resistors, I'll try to provide an insight here. Suppose you have a transformer, right? Now in a transformer, if there is a load at secondary, right, and the transformer turns ratio is N1 and N1 is to N2, so there is a load at secondary and you're seeing through primary. When you see through primary, you don't see that RL, there is some sort of a multiplication factor, right? So what is the input resistance here? It is going to be N1 by N2 whole square into RL. So this is the multiplication factor, the factor of multiplication, right? Multiplication factor. Now what is the multiplication factor if you have a BJT or a MOSFET? So you can see here, if I connect this resistance here, R or RL here, and I'm seeing through base. So if I'm seeing through base, it's going to be R pi, we know it. But what are you going to multiply to this resistor? I told you small current will give you large resistance. So you're injecting small current, it is large resistance, multiplied by 1 plus beta. But if the same resistor is at the base terminal, you're seeing through emitter, then it's going to be alpha by Gm plus this R has to be divided by 1 plus beta. So this way you can avoid all the small signal analysis and Kirchhoff's laws. See, what happens is off late, if you see gate problems, multiple MOSFET problems are given and multiple transistors. So if each transistor has 2 loops, imagine there is a 4 transistor problem, right? So you have 2 loops, so that means it becomes 6 to 8 loops. So it's difficult if you want to do by the conventional, small signal method, right? So these methods are handy. Think about it, right? So the MOSFET is also, so the MOSFET doesn't even have this multiplication because the base current is 0 in a MOSFET. So the input resistance is infinite and beta is infinite for MOSFET. Alpha is 1 and beta is infinite. So all the equations for BJT, they simply get converted into MOSFET if you substitute alpha as 1 and beta as infinite. So the resistance seen at source terminal here is going to be 1 by Gm, right? Beta is infinite. So that's okay. So these models, as I told you, they're very, very handy. So if you want to use this model, yes, you can use it and apply Kirchhoff's laws. Otherwise, you can replace transistors by resistors, right? Now the same thing here. For DC analysis, what is ID? K times of VGS minus VT whole square by 2. Because generally, MOSFET is in saturation if it has to work as an amplifier. And since the gate current in a MOSFET is 0, the gate current in a MOSFET is 0, the source and the drain current are same, so we have put an open circuit here. In an open circuit, you will have voltage but no current, right? Voltage will be manifested, but the current is going to be 0, right? And what about Zener? Now the Zener has got 3 piecewise segments here. And what are the polarities of Zener? No device has polarities. Polarities will come only with the direction of current. So if the current flows in this direction, then the Zener will have this polarity. If the current flows in this direction, the Zener will have this polarity, right? But the characteristic says that whenever the Zener is forward bias, the voltage across the Zener is a small voltage, 0.7, right? But whenever the current flows, when current flows from cathode to anode, this is actually reverse bias, right? So where is this eraser? Yeah. Okay. Now, current can flow like this. Anode to cathode, it is forward bias. Cathode to anode, it is reverse bias. So no device has polarities. Polarities will come with the direction of current. So in forward bias, you have a small voltage. In reverse bias, there is a large voltage Vz, right? So the same idea you can apply even if you have multiple Zeners like this, right? So if current flows in this direction, the Zener will have this polarities, right? And why current will flow like this? If you connect a positive voltage here, the current is going to flow in this fashion. So whenever current flows from cathode to anode, it is reverse bias. Anode to cathode, forward bias. Anode to cathode, forward bias. Forward bias means small voltage. Reverse bias means Vz. Now you can reverse the polarity of the voltage now. Now the current is going to flow in the opposite. The current is going to flow in the opposite directions, right? So these are the polarities. So if it's reverse bias, it is VZ. Forward bias, it is 0.7. So first you take the polarity, right, from the direction of current. Then you think whether it is forward bias or reverse bias. Anode to cathode is forward. Cathode to anode is reverse. Forward bias means small voltage. Reverse bias means large voltage. So, and with this simple idea, you can solve any Zener problem. And there is no special model for op-amp. An op-amp is a simple VCVS, voltage control voltage source. At the input terminals, you have a large resistance RID, and at the output terminals V0. So this is V0, this is V1 and V2. So V0 is A times of V1 minus V2. So every textbook says that V0 is A times of V1 minus V2, but this model is very specific. It says V0 is AVD only when R0 is 0. So this is true only when R0 is 0. And every book says, op-amp draws no current, but that is true only when RID is infinite. Then only the op-amp draws no current. So this model you can use and solve any gate problem using op-amp with this model. So in my opinion, this is the only thing you have to remember before going to exam. There is no, I don't think if you want, you can write some short notes and all that, but the more you practice, it is good for you, right? Because 99% of gate problems are problems, right? So there is no theory given there. So the more you do it, it's beneficial for you. And this summary is enough. Just this 2-page summary is enough, and you can go and try to solve problems. Okay. So let's see some PYQs. Just go through the problem. Now the circuit, in the circuit of the figure, V0 is, now you can see whenever the supply voltage is given, it is understood that for whatever input that you give, VD, your output is going to swing between minus 15 and plus 15. Because the output always comes from the supply. So the maximum voltage the op-amp output can hit is the positive rail voltage, and the least minimum it can hit is the negative rail voltage. Now whenever there is positive feedback, you know that it's difficult to control an op-amp. Op-amp can only be controlled in what you call negative feedback. So whenever there is a positive feedback, the output is going to hit either plus 15 or minus 15. So how do we know whether it is plus 15 or minus 15? I think there is no need to know, because if he has given minus 15, we would have checked. But he has not given minus 15, so why waste time? There is plus 15, so this is the solution, right? Now the input resistance of the amplifier shown in figure is, so how do we calculate input resistance? You will connect a test voltage VT, find IT. Find IT. So according to virtual short, this is 0 here. So you have 10K here, and here you have IT. So what is IT? IT is going to be VT minus 0 by 10K. So VT by IT is going to be 10K. So 10K is the input resistance. So 10K is the input resistance. So the series resistance is going to decide the flow of current, but this shunt resistance here, this is going to decide the voltage at the output. So now resistance here is test voltage by current. So V by I is R. This is virtually short. So there is only 10K here. 10K is the answer. in the circuit shown, what is the output voltage V out if the silicon transistor Q, if a silicon transistor Q is used and an ideal op amp are used. Now, an op amp is basically a difference amplifier, right? A differential amplifier, a high gain differential amplifier. So we know op amp works in two modes, right? So one mode is like if a positive voltage is given to positive terminal, the output is always positive. So that's the non-inverting way of operation. But if you give a positive voltage to the negative terminal, then the output will flip. It's going to be negative. So the output is going to be negative. So this simple idea can eliminate C and D options, right? So you can eliminate, because he wants the voltage from here to ground. So when I give a positive voltage to the minus terminal, your output is going to go negative. So these two are wrong, right? Now if this is a negative voltage and the diode gets on here, the diode gets on. So what is the drop here? 0 minus V naught is 0.7. So your V naught is going to be minus 0.7. So minus 0.7 is the solution, right, to this gate problem. Now consider a constant current source shown in the figure below. Let beta represent the current gain of the transistor. The load current I naught is, so where is I naught? The load is this, there should be I naught here, right? Now how do we solve this? Now this current and this current, this is the collector current. Here we have an emitter current here. Now you can see there is negative feedback here. There is negative feedback, and this node voltage and this node both are same. They are same. Okay, and this node and this node virtually are same. So this node is same as this. So this. So you can see here these 2 points are nothing but these 2 points, right? So what is the voltage between the 2 points here? The voltage between the 2 points is V reference. The voltage between the 2 points is V reference. So there is IC here. So what is I naught? I naught is IE. I naught is IE, and IE is larger than IC. So it is beta plus 1 by beta times of IC. So beta plus 1 by beta. No, this is collector current, right? So this is collector, this is emitter. This is a PNP transistor. This is a PNP transistor. This is emitter, and this guy is collector. So if it is collector, then this is a PNP transistor. So who is large now? The collector current is small, but the emitter current is large. So since it is small, beta by beta plus 1, right, times of the emitter current. And what is the emitter current here? It's V reference by R. Let us see the options. We have not seen the options here. See, emitter current is V reference by R, but he wants collector current. So collector current is smaller, so it should be beta. Collector current is smaller, so it should be beta by beta plus 1. So V reference by R. I think there is no option here. Yeah, beta by beta plus 1. So these lights are so blinding, so sometimes there's no clarity here. Okay, so beta by beta plus 1 times of V reference. Or if you don't think this is V reference, you can do the node way of doing it. So this is VCC. So this is going to be VCC minus V reference. So this node is going to be VCC minus V reference, and then this is VCC, and VCC minus V reference is V reference only. Or simple logic, this is this, right? So simple, this voltage is this. So the current is V reference by R. that is the emitter current, and op amp draws no current. So the collector current is going to be less when compared with the emitter current. So it's beta by beta plus 1 times the V reference. Okay. Now go through this problem. The following signal Vi of peak voltage 8 volt is applied at the non-inverting terminal of an ideal op amp. The transistor has Vb equal to 0.7, beta equal to 100, LED is some voltage, VCC is given, but what does he want? Oh, the number of times the LED glows. So he wants to know the number of times the LED will glow. So you all know that this LED will glow only when there is a current. And there will be a current flow only when the device is on. And the device will be on only when the output is a positive voltage. Right? So when will this be a positive voltage? When the Vi, there's a voltage divider here, 10, 8 and 2, so this is going to be 2 volt by voltage division. So this Vi should cross 2. So indirectly, we have to check how many times this Vi is going to cross 2, right, in this gate problem. So let's start here. Let me move here. This is 2. So once, again when it is going to increase, second time, and then when it is going to increase, third, right? So remember, LED is on. What do you mean by on? On means if I ask my son, right, switch on the light, switch on the light. That means the light was already off, right? The light was already off. So when he says on, you have to take the previous state as off. So it is off, off, it's on. Then from on it has become off, 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 and then on here. So 3 times. So you have to check how many times this Vi is going to cross 2 in this gate problem, okay? If the op amp in the figure has an input offset voltage of 5 millivolt and an open loop gain of 10,000, 10 power 4, then the output voltage will be. And for offset, you can model an op amp here. So you can take VOS here and the gain is given here. So we all know that V0 is A times of Vd. It is A times of V1 minus V2. V2 is already 0. So it is VOS minus 0. So it's a simple substitution problem given for 2 marks. A is 10 power 4, 10,000. VOS is 5 millivolt. 5 into 10 power minus 3, 50 volt. Now I told you, the maximum output can be plus 15 or minus 15. So since it is plus 15, it's not possible. So the op amp is going to saturate at a maximum of 15 volt. Yeah, it's given here 15. So 15 is the right answer. So V0 is A times of VOS. It's a simple substitution. A is given, VOS is given. You substitute, you get the answer, right? In the figure, assume the op amp to be ideal, the output voltage of the circuit is. So how are we going to solve this problem? Now you can take all these values and do it, but I am terrified by this calculation here, because Henry, the inductor is in millihenry and the capacitor is in microfarad. So I think we can take our chances here. You can see here, two options have integration, one option has differentiation, and one is directly proportional, right? There is no S term. So when do you get differentiation? Multiplication of S in the frequency domain is differentiation. So 1 by S is going to be integration. So let me take my chances. So I'll make this R, this is SL, R and 1 by SC. So I'll take this as Vx, and this is Vs. So what is V0 by Vs? It is V0 by Vx into Vx by Vs. So what is V0 by Vx? It's an inverting amplifier. So it is minus Rf by R. And Vx by Vs is going to be minus Rf by R. Oh. Oh, why did this come? How do we remove this notification? Okay, can you hear me? Yeah. Yeah. Oh, okay. So what I was trying to say is I'm just taking my chances here. So minus SL minus 1 by SCR into minus RF by R1. So you can see S is getting cancelled. It's a constant. There is no multiplication of S in the transfer function. So output by input, when I say there is no S term. So when there is no S term here, hopefully if you calculate, this is going to be the solution. Integration comes when there is a 1 by S, and differentiation comes when there is a multiplication of S. But here S is getting cancelled. So hopefully this is the solution, even if you try to do this. Go through the problem here once again. In the circuit shown, the op amp has a finite input impedance, infinite voltage gain and 0 offset voltage. The output voltage is finite input impedance. That means the op amp is drawing current here. But since the gain is very high, you can still apply virtual short. So you can take some current Ix here, Iy here. So you can apply KCL. So what is KCL? The current entering is current leaving. Ix equal to I1 plus Iy. So what is Ix? V0 minus 0 by R2 is going to be I1 and Iy is 0 minus 0 by R1. So that's 0. So your V0 is I1 into R2. V0 is I1 into R2. So C. So this is also given for 2 marks. Now in the circuit shown, assume the op amp is ideal. The bridge output voltage in millivolt for delta equal to 0.05 is now how do we solve this? Now you can see there is negative feedback, so you can apply virtual short. So the current here is going to be 1 by 50. Since op amp draws no current, this current should also be 1 by 50. Now what? What we can do now? Yeah, you can see here, if you add these two resistors and add these two resistors, the value is going to be same. That means it is a nice parallel connection here. 250 into 1 plus delta and then 250 into 1 minus delta. So it's 1 minus here and 1 plus here. Now these two are in series. So when you have two resistors of same value, then the current is going to divide by half. So it's going to be 1 by 100 here and 1 by 100. So now you can apply a small loop equation to finish the problem, right? A small loop equation you can apply here. So minus to plus, so minus V0 plus 1 by 100 into 250 into 1 plus delta. Then this is the opposite current, minus 1 by 100 into 250 into 1 minus delta equal to 0. So what is V0? What is V0? 250 and minus 250, they're getting cancelled. So it's 1 by 100 if I can take common. 250 into delta and 250 into delta, it's 250 plus 250, it's 500 into delta, right? So it's going to be 5 into what is delta? 0.05, 0.25. What does he want? He wants V0 in millivolt. So 0.25. So how much is 0.25 here? 0.25 is 25 into 10 power minus 2, right? So if you want in millivolt, you can divide this by 1000. So when you divide this by, so it's 25 by 1000, right? So it's 25 millivolt or 250 millivolt, we can say 250. It's 0.25, right? So 250 millivolt. assuming that the op amp in the circuit shown below is ideal, the output voltage V0 is. Now you can see here, there is no negative feedback here because this node voltage is fixed and this is fixed. So it's a comparator. It is a comparator. Non-inverting is grounded, non-inverting is 1, inverting is grounded. So whenever non-inverting is more than inverting, the output is going to be at plus 12. So plus 12 is the answer. So this is not a negative feedback problem. It would have been negative feedback if there is no ground node here. So this is a fixed voltage. So it's a comparator. So your output is going to hit the positive rail voltage. So 12 volt is the answer. An op amp based circuit is implemented as shown below. Assuming the op amp to be ideal, the voltage in volts correct to 1 decimal connected at the negative input indicated in the figure. So what does he want? Okay, so he wants this node voltage A, right? Now this is an inverting amplifier. So what is an output here? Minus R2 by R1, minus 31 by 1 into 1, so output is minus 31. So but you can't get minus 31. The maximum voltage you can get is only minus 15. Right? And since it is an inverting amplifier, the output has to be negative. But he wants this VA. Now you can apply superposition if you want. Right? Since op amp draws no current, you can apply superposition if you want. So there is 1 volt. And there is minus 15 here. So here there is an op amp draws no current. So this is a simple network. So what is VA? If I short this, VA is going to be 1 into 31 by 1K plus 31 is 32. And if I ground this, this is going to be minus 15 into 1 by 32. K will get cancelled, however, right? What is 31 minus 15? I think 16 by 32. 16 twos are, right? 0.5 volt. 0.5 volt is the solution, right? So you can do it here also, but okay. So this node voltage due to 1 volt is 1 into 31 by 32, and this voltage due to minus 15, if you backtrack, this is ground, minus 15 into 1 by 31 plus 1. So you can get, or you can do the nodal analysis here, right? Entering current equal to leaving current. If you have patience, you can do the node method and solve, right? Okay, the components in the circuit given below are ideal. R is given 2K, C is 1 microfarad. The 3 dB cutoff frequency of the circuit in hertz. Now how do we do this? Now you can see here, if this is ground, this node is 0, right? So what is the current flowing here? So these two are dummy. No current is going to flow. So if there is any capacitor that is going to decide the cutoff frequency, it is this capacitor, right? So your F is simply going to be 1 by 2 pi RC. Now these two are dummy, just for time pass he has given, because no current is going to flow here, because this node is 0 and this node is 0, and current needs a potential difference, right? So it is 1 by 2 pi, pi is 3.14 I think, so we'll make it 3 for the time being. R is 2K, C is 1 micro. So it's going to be 1000 by 12. So what is the answer here, which is nearing to 1000 by 12? 1000, what is 12th table? 12 sevens are 84, 12 eights are 96, 12 eights are 96, right? So something that is close to 82, 83 you'll get. But as I told you, these options, if you see, they are widespread, right? So I made 3.14 as 3, so it's getting close to 82, 83, so hopefully this is the solution, because you have 79 there, right? So try to make a little approximate analysis, especially when the options are widespread. You don't have to take 3.14 and then waste time. The magnitude of the midband voltage gain of the circuit shown in figure is assuming HFE of the transistor to be 100. So he wants the gain, the voltage gain of this circuit, and nothing is given, only beta is given. So if you draw the AC equivalent, this is the circuit. So what is V0 by Vin? So here you have IC, this is IB, and here there is VB. So V0 by Vin, V0 is minus IC into 10K, Vin is VB plus IB into 10K. Now divide numerator and denominator by IC. So what do you get? Minus 10K by IB by IC is 10K by 100 plus VB by IC. VB by IC generally will be 20-25 ohms, right? So you can neglect this value. So 10K gets cancelled. So this one I am neglecting. 10K gets cancelled. The answer is close to minus 100. So yeah, 100 is here. It's close. Actually, you don't get 100, but here, see, that is the good thing about gate problems. If you do the actual calculation, you might get close to 85, 86, but directly 100 he has given. So there is no need for you to do DC analysis, because if you do DC analysis, you get this extra term 1 by GM, right? 1 by GM here, but I neglected that 1 by GM, 20-25 ohms, we have neglected it. So directly we are getting an answer close to 100, right? The value of R for which the PMOS transistor in the figure will be in linear region. See, what do you mean by linear region? In linear region, MOSFET will work as a switch, right? So this voltage should be small. If this voltage has to be small, this drop should be large. When will this drop will be large? When the resistor is large, right? So many options are given. So we'll check 1 or 2 resistors and see. What if this is 680 ohms here? 680 into 1 milli is 0.68. So 4 minus 0.6 is going to be 4 minus 0.6 is 3.4, but your VGS or VSG here is 4. VT is, VT is 1. So this is 3, this is 3.4, it is still in saturation. In linear region, this value should get less when this drop is more. So I think 1200 is the only option, right? Because for this resistance itself, it is in what region? Saturation. Here it will definitely be in saturation, but I think this is the answer. But let me try. What if I put 1200? So this will be 1.2. Yes, correct. 1.2. So you will be left with only 1.8 here. So this voltage is very less. So definitely it will go to the linear region or triode region, right? Linear is also called triode. So it's don't try to solve this. So just substitute and see, right? Oh, I wanted to do MOSFETs, but again BJT has come. So we'll try some MOSFET questions. Okay, what is there? The common emitter amplifier in the figure is 1 milliampere. The approximate base current is, see, emitter current is given. What is base current? This is a lollipop question. IB is going to be IE by beta plus 1, 101. So you can make it 100. 1 milli by 100, 10 micro. So it's 10 micro here, approximately, right? So we'll try MOSFETs, that is better. I'll just check. The transconductance GM of the transistor is given, the value of input resistance. See, I told you the resistance reflection rule, right? For AC analysis, this is ground. So these two will come in parallel, 10K, parallel with 10K, and then the BJT. Now here if you cut, you will have R pi here. If you cut, you will have R pi. We have to calculate R pi from GM, right? But what is 10K parallel 10K? It is 5K. So now you have to calculate. See, there is no need to calculate also. Please see here. Whenever this extra R pi comes with 5K, the resistance will decrease, right? So in parallel, resistance will generally decrease. So your answer should be less than 5K. Your answer should be less than 5. So in the see the options here, 5K, less than 5K is only this. So you don't have to do this, right? Because the transistor is going to offer some resistance. 10K parallel 10K is 5. So 5 parallel with something. So that naturally it's going to be less than 5. So there's no need to do this. Already 2.5 is there. So that's an option. So I wanted to do some MOSFET. Yeah, this is also a good problem. The relaxation oscillator is made using op amp. The supply voltage, there is some printing gone. The supply voltage of the op amp is, and the voltage waveform at point P. Now see here, this is a relaxation oscillator, which is a square wave generator. So when this is square wave, naturally the resistor divider will also give you a square wave here, because resistors will never change the shape. So yeah, so these two are wrong. These two are wrong. So now we are left with two more options, right? Out of these two, which one is correct? But here some voltage should be given. Okay, no problem. Now just see the divider here. Suppose you take X volts here. X volts, whenever this diode is on, it's going to be half, 1/2, right? Now here there is 2K here, 10K here. Whenever the negative side, this voltage, this diode is on, you're going to get more voltage here. So less voltage in positive, more voltage in negative. So that's the analysis, right? Because 2K is there, 10K is there. So more voltage in negative side, less voltage in positive. So otherwise we would have calculated that printing is gone. Now you can see here in these two, more voltage in negative and less voltage in positive. So this is the option. So if you want, you can take something here also. And 10K, 10K, you're getting 6. So that means this is 12 actually. So even if it is something else also, no problem. So less voltage in positive, more voltage in negative. So through the process of elimination, that is the solution, right? Okay. Again, diode has come. Still, we'll do one or two MOSFETs. MOSFETs I have tried a little. Yeah. In the circuit shown in figure, both the NMOS transistors are identical. Threshold voltage is given, ignoring the channel length modulation, the output voltages. See, this is a simple problem. Whenever ID is proportional to VGS, right? ID is proportional to VGS. So two MOSFETs, if they have same ID, they have same VGS, right? So this is a MOSFET which has same ID because it's in series. So naturally, if this is 10, this is also going to be 10. But here there is a 30 volt here, right? 30 minus 10 is going to be 20. 20 is the solution for this 2 marks problem, right? So two MOSFETs have same ID when they have same VGS. Since the gate and drain are shorted, this voltage is 10, this is also 10. Because G and D are same, so VDS is VGS. VGS and VDS, because D and G are same, right? So it's 20. Any MOSFET here? MOSFET. Oh my God, this one is a very good problem. Now see here, the input signal is shown in the figure, is fed to a Schmitt trigger, and the signal has a square wave of 6 volts. It is corrupted by a noise. See, there is a square wave here. It is corrupted by noise, right? So now he wants you, it is corrupted by noise, and what does he want? Which one of the following is an appropriate choice of upper and lower trip points? So he's asking you in a Schmitt trigger, suppose this is the hysteresis. This hysteresis characteristics in a Schmitt trigger is called the noise margin. In digital, we call it noise margin. So that means there should not be any noise affected in the signal which should cross this margin. And he is giving 4 margins here. Plus or minus 0, plus or minus 0.5, plus or minus 2, plus or minus 8. There should be not a single noise signal which crosses both this plus 2, minus 2, plus 8, minus 8, plus 0.5, minus 0.5. So let's see, where is this noise here then? Yeah. What if I take plus 8 and minus 8? First of all, there is no signal, right? The signal is stuck in between. It has to cross above UTP, below LTP. So you can't take here. There is no signal, there is no noise there, right? So that is wrong. This is wrong. What if I take plus or minus 0.5? If I take plus 0.5 here, minus 0.5 here, you can see that noise is crossing. What the margin of safety is, it should never cross the UTP and LTP, but it is crossing here. Now what if I take plus 2 and minus 2? Plus 2 and minus 2. Just check, is there any noise, a single noise signal which is crossing? This one is going up, it's not crossing minus 2. This one is crossing minus 2, but it's not crossing plus 2. I think plus or minus 2 is the right answer, this one. Plus or minus 0.5, this is wrong. 0, of course, is wrong. 0, 8, both are wrong. So now the choice is only in these two. So this is a very good problem, right? Logical. Oh yeah, there is one MOSFET problem. I think this should be parallel. Now this is a current mirror circuit. You have 1 milliampere here. So this guy should be 0.5, 0.5, and this is 0.5. But what does he want? He wants current here. This current is going to be 0.5. So that is this solution. And let me read it. What does he want? The current IS he wants. So that we have calculated what is there. So this current 1 milliampere is split here. So this 0.5, that's it. Then why did he give this? See, there are, it's a linked question. A bit is this, but B bit is also here, right? What is B bit is, for the computed value of IS, the output voltage is. So here 0.2 milliampere current is flowing like this. Current is flowing in this direction, so naturally this diode is on. This diode is on. Whenever diode is on, it takes a drop of 0.7. And how much current is flowing here? 0.5 milli. So this is 0. So what is V naught minus 0? V naught minus 0 is going to be this drop plus this drop. 0.7 plus 0.5 milli into 1K is 0.5. It is 1.2. 1.2. So that's the solution. Any other MOSFETs? No. If the op amp in the circuit shown are ideal and Vx is 0.5 milli, this Vx is given 0.5 milli. What does he want? The steady state output V naught is, I think this might take time. He wants V naught. Op amp draws no current. So this is 0. So this voltage is also 0. So what is this node voltage? Suppose if it is VA, VA minus 0 is Vx. That means this is Vx only. Vx minus 0 is Vx. And since op amp draws no current, you can take a simple voltage division here. Vx is given. Vx is 0.5 millivolts. So give me a voltage division. It is V naught into 100 by 100 plus 99.9K. So that's 100K. So 100K into 0.5. What is 100 into 0.5? 100 into 0.5 is 50. So 100 V naught is 50. V naught is 50 by 100 is 0.5 volts. 0.5 is the answer. Yeah, I think my cameraman says the time is already 8 o'clock. Maybe we'll take one more. The value V naught of a series regulator is. Now you can see, according to virtual short, if this is 6, this is 6, right? And same current will flow. Now across 2K, if there is 6, across 8K, there should be 4 times of 6. So what is 4 times of 6 is 24. So V naught is 24 plus 6, it is 30 volt. This is the solution. Or you can take some current here. The current I is going to be 6 by 2K, which is 3 milliampere. So 3 into 8 is 24. So your V naught is going to be, 30 volts. So this is the solution. So like that we can keep on solving. Okay, right? So all the best. My good wishes to you, right? So this is my phone number. So if you wish, you can WhatsApp on this number if you have doubts. Okay, good luck.